Now that we've established the existence of Nash equilibria, but found that our proof techniques were non-constructive, it's time to think more deliberately about how we can compute Nash equilibria in general. So in this video, I want to explore some algorithm approaches inspired by ideas we've already seen. And the first of these ideas is to simply follow the Nash advantage function until it reaches a fixed point. Since the advantage function takes one profile as input and produces another profile as output, where it has tried to nudge the probabilities in a direction that will be beneficial for each player, we might reasonably think that by applying the advantage function over and over again, we could continually nudge the profile to be better until we get close enough to a Nash equilibrium. But unfortunately, the advantage function is not at all well suited to that task. There's no theoretical guarantee that repeated applications will approach a fixed point, and that very much tends not to happen if you try this in practice. But it is worth taking a moment to think about why this approach goes wrong. For one thing, when we compute the advantage function, we add to each probability the gain of that action. And those gains can be quite large numbers, which will result in wild swings in the probability as we take steps according to this function. And so if the function is leaping almost arbitrarily around the symplectope with each step, there's no particular reason that it's ever going to get close to a Nash equilibrium. But it's also possible that even if it does get close to a Nash equilibrium, the basin of attraction of that equilibrium will be quite small. And only profiles that are very near the equilibrium will actually be pushed to the equilibrium by the advantage function, and over some small distance away, profiles will actually end up being pushed away from the equilibrium. And it's even possible for that basin of attraction to be just a point, where no matter how close you start to the equilibrium, the advantage function will push you away. And it's entirely possible for repeated applications of the advantage function to get stuck in a loop that goes around or is nowhere near an actual fixed point. But even if repeatedly applying the advantage function doesn't get us very far, we know actually a lot more about the advantage function and its fixed points from Sperner's lemma. And this leads us to a second idea for an algorithm, which is to modify the approach we were trying to take in our proof last time, so that we do an exhaustive search to find our fully labeled subsimplex. And then we know we can zoom in on that fully labeled subsimplex and eventually narrow in on an equilibrium. But there are a number of complications here. First is that in general, equilibria don't live in a simplex, they live in a much more complicated symplectope. And so we have to extend our simplicial subdivision into a triangulation of the symplectope. And if we're going to exhaustively search over the vertices of that subdivision to try and find a subsimplex that's completely labeled, then we should really think about how much work are we doing at each iteration when we perform the subdivision, label all of the vertices, and find something to zoom in on. And if we start by thinking about just a single player's strategy simplex, if they have two actions, then when we subdivide the simplex, we could get only two subsimplices. But if they have three actions, then the simplest subdivision we could do gives us four subsimplices. And with four actions, the smallest possible simplicial subdivision gives us 8 smaller tetrahedrons. And so hopefully the pattern here is obvious, that as the dimension of the simplex increases, the number of subsimplices is growing exponentially. In each of these examples, I've divided each dimension of the subsimplex in 2, but in general we could do a d-way subdivision on each dimension. And if we divide d ways, then our number of subsimplices will be d raised to the dimension of the original simplex. But remember, this is just the subdivision of one player's strategy simplex, and if we have many players, then in general, we will have to subdivide the simplitope that comes from the product of all of their simplices. And as I've illustrated here, if we take those two simplices, in this case just two actions for each of the two players, then our subdivision of each simplex into two gives us 4 sub-simplitopes. And so the number of sub-simplitopes is the product over all of the players of the number of sub-simplices when we divide their simplex. And so even assuming that we do the simplest possible subdivision, dividing each dimension in half, we will get a number of simplitopes proportional to 2 raised to the total number of actions in the game across all players. But in addition to having exponentially many subsimplitopes, it turns out that the algorithmically useful extension of Sperner's lemma to simplitopes requires that we turn the simplitope into a triangulation of simplices. And so we'll have to split up those subregions that come from the product further still to turn each region into a simplex. So the overall message here is that if we have any non-trivial number of players and actions, then every time we try to subdivide the simplitope, we're going to have an enormous number of subdivisions to consider. And remember that in the worst case, we'll have to explore every single vertex of the subdivision before we find a completely labeled subsimplex. And to compute the label for any vertex of the subdivision actually requires computing expected utilities to evaluate the advantage function, and those expected utilities are a summation over the entire payoff matrix, which itself grows exponentially in the number of players. And so, while algorithms based on simplicial subdivision can in principle correctly identify Nash equilibria, they tend to be extremely inefficient on all but the smallest games. And so it's worth thinking about whether any other approaches might help us more efficiently identify Nash equilibria. And so if we think back to when we first introduced the concept of a mixed strategy Nash equilibrium, we found an equilibrium of the penalty kick game by solving a system of equations. And so maybe there's some sort of approach that generalizes that notion of solving systems of equations to find the probabilities for mixed Nash equilibria. So the algorithmic approach here would be to take the payoff matrix and, based on those utility values, construct the appropriate equations to solve. And then it turns out that solving systems of equations is a very well-studied topic, and there exist very powerful algorithms for solving certain sorts of mathematical optimization problems. Specifically, if we can formulate our problem as a collection of linear equations, then we can solve it with linear programming, which can be done very efficiently. But if we end up with nonlinear equations describing our Nash equilibrium problem, then it turns out that nonlinear optimization is a dramatically harder problem and won't generally serve as the basis of an efficient algorithm. So if we return to the equations that we wrote for solving the penalty kick game, to find the probabilities P and Q that the kicker used to randomize their action, we wrote equations capturing the requirement that the goalie be indifferent between their actions. So the expected utility when the goalie chose jump left has to be equal to the expected utility when the goalie chooses jump right. And likewise, we could solve for the goalie's probabilities by an equation that forces the kicker to be indifferent. And by solving each of these equations, we got probabilities PQ for the kicker and AB for the goalie, that we could then verify constitute a Nash equilibrium profile. But if we tried to set up the same sorts of equations for other games, we might run into a problem. Specifically, if we look at Prisoner's Dilemma and try to solve for the probabilities P and Q that player 1 could use to make player 2 indifferent between their actions, then we'd have an equation that 2p plus 0q is equal to 3p plus 1q, and with the constraints that p and q have to be a valid probability distribution falling between 0, 1 and adding up to 1, there is no way to make the two sides of this equation equal. And so if we gave this collection of equations to a linear programming solver, it would tell us your linear program is infeasible. There's no way to set the variables to make all of the constraints hold at the same time. And in the case of Prisoner's Dilemma, what that means is that there isn't a mixed strategy Nash equilibrium. The unique Nash equilibrium of Prisoner's Dilemma is for both players to play the pure strategy defect, and when they do that, they're not indifferent between their actions. If the other player is playing defect, I have a strict preference for defect over cooperate. And so it is correct to say that there is no solution that makes me indifferent. And this is true in general of a 2x2 game. If we write down a linear program and try to solve it, and it turns out to be infeasible, that means that the only Nash equilibrium is a pure strategy equilibrium. But if we move to an example of a 3x3 game, where here we have the extension of the penalty kick game, where the kicker can kick straight and the goalie can not jump, then if we write down our linear program for the players being indifferent between all three strategies, that gives us these systems of equations. The probabilities P, Q, and R for the kicker have to sum to 1, and each one individually needs to be between 0 and 1. And then we need that the goalie should be indifferent between jump left and jump right, expressed by this first equation, and they also need to be indifferent between those and don't jump, expressed by the utility of jump left being equal to the utility of don't jump in the second equation. Likewise, for the goalie's probabilities A, B, and C, they need to be between 0 and 1 and sum to 1. And we need that the kicker is indifferent between kick left and kick right, and that the kicker is indifferent between kick left and kick straight. And once again, if we were to give this set of equations to a linear programming solver, it would tell us the linear program is infeasible. There's no way to set these probabilities that meets all of the constraints that we've given. But in this case, we can't conclude that there's a pure strategy equilibrium like we could for Prisoner's Dilemma. That was specific to the case of a 2x2 game. Here, the reason there isn't a solution to this linear program is that the Nash equilibrium doesn't have full support. In fact, we already know what the Nash equilibrium is. It's 0.4, 0.6, 0.7, 0.3, and then both players playing a probability of 0 on their extra action. But the way we would come up with those probabilities using linear programming in a way that's generalizable to any 3x3 game is that we would have to generate separate linear programs for the different possible support sets for each player. So we might start with the support set of all three actions, and when the solver tells us that program is infeasible, we would move on to exploring different combinations of a subset of the strategies being in each player's support. So here I have a set of equations that corresponds to kick left and kick right being in player 1's support, and jump left and jump right being in player 2's support, while the other actions have probability 0. And now the probabilities that player 1 is choosing have to make player 2 indifferent between the things in their support. So we have just the first equation that the goalie is indifferent between jump left and jump right, but it also needs to be the case that actions outside the support aren't beneficial deviations. So the expected utility that the goalie gets from one of these actions has to be at least the expected utility that they would get from playing the action outside the support. And so we say that this expected payoff is greater than or equal to the one for don't jump. Likewise, for the goalie's probabilities, we want to make the kicker indifferent between the things that are in their support, and we want the things that are not in the support, playing kick straight, to be no better. And solving this linear program would give us the same probabilities that we got from the 2x2 game, and so this gives us a Nash equilibrium. But in general, we would need to try all possible combinations of support sets for the different players. And how big are those support sets? Well, the support can be any non-empty subset of the actions. The number of subsets is 2 to the number of actions. And we can rule out the empty subset because they have to be playing something. And we can also rule out the subsets where they play only one action, because that would be a pure strategy equilibrium. And we know that it's much easier to search for pure strategy equilibria separately. So, in this case, we would search over all possible combinations of 2 or 3 strategies for the players. So, considering just the 2 action support sets, we have 3 choose 2 possibilities for each player. Since 3 choose 2 is 3, there are 3 different 2 action support sets, and there is the 3 action support set. And so we have potentially 4 different support sets for each player, and a total of 16 different combinations, where in the worst case we might have to try all 16 different linear programs before we found one that gives us back Nash equilibrium probabilities. So this case, where we have more than 2 actions and we don't know exactly which actions will be in the support set, is an example of a linear complementarity program. When we're actually solving the equations, all of the equations are linear. We have constant times a variable plus constant times a variable for everything in these equations. So everything is linear, but we don't know exactly which set of variables we should be solving over. So we can use an efficient linear programming solver to check each possible combination of support sets, but as the number of actions grows, our number of possible support sets grows exponentially. And worse yet, we've still only considered the case of 2-player games. So what would happen if we tried to apply this approach to a game with more than 2 players? Here I have our simplest possible 3-player game, and I've only written in payoffs for player 1, because that's enough to illustrate the problem, which is that when we try to write down the equation that player 1 is indifferent between their 2 actions, we have to write down the expected utility for their first action is equal to the expected utility for their second action, and the expected utility depends on the probability of each outcome happening, and the probability of this outcome is the product of the probability A that player 2 assigns to the column, and the probability X that player 3 assigns to the matrix. And so all of the terms in this equation involve a product of two variables, one for player 2's probability and one for player 3's probability. And because we have a product of variables, this is a nonlinear equation, and so our optimization problem is now nonlinear, and so we can't in general expect that mathematical optimization can solve it efficiently. So in some sense, this is a pretty sad outcome. All three of our ideas either failed or gave us algorithms that are going to be very inefficient in the worst case. But there is some potential hope here in that certain cases turned out to be efficiently solvable, or at least somewhat manageable. And so next time we'll focus in on linear programming in particular, and think about what sorts of equilibrium computation problems can we solve efficiently by turning them into linear programs.